Yo, what up, y'all? Hope you're having a wonderful day. I'm here with the inverses and logarithms practice test, trying to help you for that test that's coming up on like Tuesday, Wednesday. If you're looking for inverses, you might want to skip to the end of the video. There's some inverses on the very bottom of the back page. We'll do some of those. If you want more inverse practice, I know there's only 2 on here. If you want more inverse practice, you can just look it up on YouTube. There's a lot of great videos on inverses on YouTube. Let me put my name on this. Okay, so for logarithms, one of the most important things to know is that a logarithm is the inverse of an exponential, which means that they are opposites of each other. They like undo each other. So there's a lot of converting between logarithms to exponentials, exponentials to logarithms to like solve equations and things. What you need to remember is that they each have the same 3 parts. They each have a base, an exponent, and an argument, also called like an answer, and they just appear in different orders. So for a logarithm, it'll say log, and then it will give you a base below that. The number right next to that base on the same level as the log is called the argument, and then that is equal to an exponent e. So I'll label these things. Argument, also called the answer, and then this is the exponent. So the way a logarithm works, I'll use this one for an example. Log base 4 of 16 gives me the base and the argument or the answer. So my base is 4, my answer is 16. So this log is saying, okay, the base is 4. What is the exponent required to raise 4 to be 16? So that's why log base 4 of 16 is equal to 2, because that is the exponent required to raise this base of 4 to give me this answer of 16, for example. Okay, so there's going to be a lot of converting back and forth. An exponential is the same 3 parts, the base, the answer, and the exponent, but they're just arranged in a different order. An exponential will give you the base, like this is the base of 3 in this exponential. Then it will give you the exponent. So 3 raised to the 4 is the exponent. And that is equal to the answer, and that shows up as the argument here for the log. So right here, I've got an exponential equation. So it's in the form of b to the e equals a base raised to an exponent equals an answer. So 3 is my base. Looks like 81 on this side over there is my answer, or my argument, and that 4 is my exponent. So if I want to convert this to a log, all I do is I take that b, e, and the a, and I rearrange them in this form. So this will be log base 3, my a, my argument, or my answer is 81, and that is equal to my exponent of 4. So that's perfect. These are equivalent expressions, just different ways of writing them. This one gives you the base and the exponent first. This one gives you the base and the answer first. So just different ways to write it. And then more commonly, you'll go from like a log to an exponential. So this is log. I like to remember. I love logs. Log is bay. So that'll remember, okay, B, A, E. So this is my B. This 16 is my A, my argument, or my answer. And this 2 is my exponent. So if I want to write it in exponential form, all I got to do is rearrange those things. So my base is 4. Next is the exponent, which is 2, equals the argument, or the answer, 16. Just like that. Cool. Cool. Okay, to evaluate this log, we just got to know what it's giving you. So it's giving me the base of 4, and it's telling me that the answer is 64. So this is asking 4 to what power will give me 64. 4 is the base, 64 is the answer. I'm looking for the exponent required to make that happen. 4 to the first is 4. 4 to the second power, 4 times 4 is 16. 4 to the third power, 16 times 4 is 64. So log base 4 of 64 equals 3. because 3 is the exponent required to take 4 and raise it to the power of 3 to give you 64. That's how that works. Okay, same thing here. My base is 3. I'm wondering what exponent do I have to raise 3 to give me this argument of 1 over 81. The fact that it's a fraction 1 over 81 tells me that it's going to be a negative exponent. So what I like to do is I ignore the fraction for a second, and I'm like 3 to what power gives me 81? And then since it's a fraction 1 over 81, it'll just be negative. So 3 to the first is 3, to the second is 9, times 3 is 27, times another 3 is 81. So 3 to the fourth is 81, but I want 1 over 81, so it'll be negative 4. 3 to the negative 4 is 1 over 81. So just evaluating log base 3 of 1 over 81, it is negative 4. Cool. Okay, and then in this case, it's giving me a log with a base 25, so 25 raised to some power. My answer that I'm looking for is 5. I know it's not 2. 25 to the second is way too big. We were just talking about negative exponents. 25 to the negative 2 would just be 1 over 25 to the positive 2, so that's also way too big. So I know it's got to be this one. When you have a fraction as your exponent, this is like 25 to the 1/2. If you have a fractional exponent, I know this is kind of small, the numerator is an exponent, the denominator is like a root. So this would actually be 25 to the first, and then since this 2 is on the bottom, it's actually the same as a square root. So that's why it's 1/2, because 25 to the 1/2 is the same as square root of 25, which will give you 5. So 25 to the 1/2 gives you 5. Cool. If you want to evaluate this one, I don't like that. That negative 4 is there. There's multiple ways that you can solve this, but I like to use the power property of logs and move that negative 4 from the exponent to the front of the log before I evaluate anything. So just like that. Now it'll just be negative 4 times whatever this is. My base is 5. Log base 5 of 25 is asking 5 to what power gives me 25. And that'll be 2, because 5 to the second is 25. Sorry about the focus. There we go. So negative 4 times 2, this would be negative 8. Cool. Okay, yay. Expanding and condensing. And then what do we got? Okay, cool. So expanding and condensing. When you're expanding a log, you're taking one log with like a complicated looking argument and you're splitting it up into a bunch of different logs. And then when you're condensing, you're taking multiple logs and you're condensing them or combining them into one log that kind of looks something like this, where there's a more complicated argument. I'm going to do the condensing first, actually. Now that I look at this. To condense these logs, I'm going to use that power property that I just used here, but in the reverse way, where I'm going to take these numbers from the front, and you can move those to be the exponents on these arguments of x and y. So it'll become log base 5 of x squared, so that 2 just moves from there to the x squared. And then that 4 will move to become an exponent on the y. And then when you have two logs being added together, you can condense them into one log. Since these are log base 5, my one log will be log base 5. And then I will take these two arguments and multiply them. So x squared, y to the fourth. If these two logs were being subtracted, it's very similar, except that now these arguments would be divided. And we'll see what that looks like up here. All right, I'm going to jump around. I'm going to do the expanding ones now before I do this condensing. So if I am expanding this log, I notice that in the argument there's a bunch of multiplication happening. So it's kind of the opposite of this. It's going to be multiple logs being added together. And each log will get one piece of this argument. So I'll do this step first. This will be log base a of x plus log base a of y plus log base a of z to the third. I just took that argument and split it up into 3 parts, all being added together. But then that 3, the power property, in order to fully expand, you have to move that 3 to the front. So I'm going to write this at a bit of an angle, but it'll be log base a of x plus log base a of y plus 3 log base a of z. And that's fully expanded. You have to move this exponent to the front in order for it to be fully expanded. Cool. This one, now in the argument, instead of multiplication, these are being divided. So instead of adding the logs, these will be subtracting. So I'll start with log base x of a to the third minus log base x of b. 2 logs being subtracted. The first one gets the top, the second one gets the bottom. All I got to do to fully expand it is take that 3, move it to the front, and that's good. I guess I'll box this one too. Alright, I'm just grooving. I am locked in. Okay, so in order to condense, I've got to power property, take any number in the front and move it as an exponent. And then I have a multiplication happening, or I have an addition happening and a subtraction happening. So it looks like these 2 arguments are going to be multiplied, and then this one's going to be divided. So I'll rewrite the power property first. And then how do I condense these? I'll multiply a to the third times b. They're all going to be in 1 log. A to the third is being multiplied by b, since these 2 logs are being added. But then this log of c is being subtracted, so that one gets divided. It's like a combination of both of these. Okay, sweet. If I want to condense these, I would take these 2 numbers and multiply them. So log base 3 of 6 times 4.5, which is 27. And then now that I condensed it, this is very solvable. This is 3 to what power gives you 27, and that would be 3 to the third. So this is equal to 3. Because if I condense them, it's log base 3 of 27, which is 3. Okay, this time they're being subtracted, so I will take those arguments and divide them. I'll make it clear by doing that this time, which will give me log base 2 of 16, which is asking me 2 to what power gives me 16, and that'll be 4. 2 times 2 is 4, times another 2 is 8, times a fourth 2 is 16. Bada bing. Okay, I'm doing this during ELP. We've got 10 minutes left of ELP. I've been going for 13 minutes. I think I can do this whole page in 10 minutes, so it's not awkward when the bell rings. Okay, and this is a video, so you can slow it down. I think I can afford to go a little fast. When you have change of base, if you have a log with some base that you don't want, usually the case is we're trying to put this in the calculator, but the calculator only does base 10. We can change the base. There's a whole algebraic process that will give you this proof, but you can just remember that you take log of the argument right here divided by log of the base, and then that will be able to put in the calculator. You can make this whatever base you want. Usually we're going to do base 10 because it's a calculator. So log base 8 of 4, you'll see how easy this is. It's just log of 4 over log of 8. And then you could put that in a calculator. So log base 5 of 30 is log of 30 divided by log of 5. To solve these logarithmic functions, what you need to do is what we did right here. Where are we at? Where I'm taking this log and I'm converting it to an exponential, just like this, using the b, e, and a. And then when you do that, you'll be able to solve for this x now. So this is the b, base 2. I have an argument of x minus 5 and an exponent of 3. So if I rearrange that in the order of an exponential, which is b to the e equals a, it'll be 2 to the third equals x minus 5. Cool, and now that is a very solvable equation. 2 to the third is 8. So I have 8 equals x minus 5. Add 5 to both sides. X is 13. Bada bing. I do not know how to solve this equation without converting to an exponential. Cool. Okay, for this one, let's see. I'm like so used to power property that I like to move this x, or I like to move this 2 to be an exponent on 4x. Some people divide by 2 to start off. You can totally do that. Whatever you prefer. But I like this way. And then now it's very clear. Okay, this is my base. This is my argument, 4x squared. And this is my exponent. So I will convert it right away, just like this. And then this might seem a little tricky. 4x squared is 4x times 4x. So these 4's get multiplied to give you 16, and these x's get multiplied to give you x squared. So 4x squared is 16x squared. 4 to the third is 64. Bada bing. So we have a very solvable equation. You can divide by 16 on both sides. That will give you 4 equals x squared. You square root both sides. X equals 2. And then maybe or negative 2, but we'll talk about it. There's some contexts that get plus or minus, and there's other contexts that don't. Let's just leave it at that. Okay, creating an exponential equation for these situations, what you got to do is you will have a starting value. Hey-yo, 1 second. And we're back. Okay, I'm back. Okay, so when you're making an exponential function for a situation, you will have a starting point, and you will multiply that by like some growth factor. Like when we did the penny, we started with a penny that was doubling every day, so we multiplied it by 2. And since it was doubling every day, that doubling got the exponent because it's happening repeatedly. So you have a starting point. How much are you growing or decreasing by? And that's happening repeatedly, so it gets an x. Okay, so right here, it sounds harder than it is. You'll see. Right here, I have an investment that grows at 11% per year. Calculate its value after 5 years. Let's say y equals, I'm starting with $100. That is growing by 11% per year. So if it's growing by 11%, it's starting at 100%, at $100, and then it's adding 11% more. If I convert each of those to a decimal, it's 1 plus 0.11, so it comes out to 1.11. And then to the power of x, because that is happening repeatedly. So to increase by 11%, I multiply by 1.11. Very cool. And then this is saying, what is its value after 5 years? The x is years. So after 5 years, I just plug in 5. Oh my god, you can see I'm kind of like fading. I've been doing this for like 20 minutes. And then you put that in a calculator. Let's see what we get. 100 times 1.11 to the power of 5. That $100 after 5 years of increasing by 11% a year is worth 168 and about 51 cents. Cool. All right, I'm gonna try to speed. This one is increasing by 8% a year. So I'm gonna take 100% and add on 8%. 8% as a decimal, you take that and you move it 2 to the left. So it's 0.08, not 0.8. So 1.08 is what I multiply by to increase something by 8%. So I am starting with a painting that is $2,000, and I am increasing by 1.08 every year X. If I want to know how long it'll take to be worth 5,000, X is the amount of years, so I'm not going to plug it in. That'll tell me how much is worth in 5,000 years. I'm going to plug it in for the value on the left, because my Y stands for how much the painting is worth. So I'll plug in 5,000, and this will tell me when it's worth 5,000 if I solve for X. So to solve for X, I first get rid of this 2,000 that's being multiplied by this 1.08 to the X. And that'll give you 5 over 2 equals 1.08 to the X. And then just like when we were solving log equations, I immediately took this log and I converted it to an exponential. I'm going to take this exponential and I'm going to, let's see, there's two main ways to do it. How do we want to do it? You can either convert this to a logarithm, because we have the base, we have the exponent, we have the answer, or we could take the log of both sides. Let's take the log of both sides. So if 5 over 2 equals 1.08 to the X, it is mathematically legal to take the log of both sides and say log of 5 over 2 equals log of 1.08 to the X. And what that does is that allows you to power property move that exponent to the front of the log. Just like I did here, and I moved that 2 from the front to become an exponent, you can move that X to the front. And the reason that we take the log of both sides is because that allows the X to leave like this land of exponents, and it goes to the front. And now it gives me something that is very solvable. So this is getting a little crammed, but I have log of 5 over 2 equals now X log of 1.08. All you got to do is divide by log 1.08. And then we got it. X equals log 5 over 2 over log 1.88. If you solve it the other way that I was talking about, where you convert this to an exponential, you'll end up getting the same thing after you change the base. So if I put that in a calculator, what do we get? We got to be careful that we like close parentheses and everything. Log of 5 over 2, close parentheses, divided by log of 1.08 will tell us how many years, how long exactly it takes for this painting to be worth $5,000. And it takes 11.906 years. If it increases at 8% every year, it takes exactly this long to be worth 5,000. Cool. Okay. That bell's about to ring. Called it. Called it. All right, I'm going to pause it for a second, and I'll do these inverses. All right. So an inverse function, here's a function, f of x equals 3x minus 5. The inverse function of f of x, I like to call it like the perfect opposite. Whatever this function does, the inverse function will undo. So hypothetically, if this was a function where I plug in x an amount of time and it tells me the output of distance, if I make the inverse of f of x, what that will allow me to do is I can tell it an amount of distance where I'm plugging in the opposite thing. I know this is getting confusing. And then it'll tell me the amount of time. So the inputs and outputs flip-flop. It's really useful for solving problems. We'll see how. Okay. Okay, whatever. Oh, Alexander. Oh my God, I'm getting crazy. 23 minutes in. How long it takes me to like lose my mind talking to myself. Okay, so 2 ways of doing this. I'll do both of them. Y'all seem to really like the swap x and, or not the swap x and y, the do and undo method. So you make a 2-column list, one do, one undo. The do column is what happens to the function in the original, and then we undo that. Let's see. So for the do column, you look at the x. I like to say I pretend that I am this little x. What happens to me first? I get multiplied by 3. Following PEMDAS, that's the first thing that happens. And then the minus 5. Bada bing. So those are the 2 steps of the function. To make the undo steps has to be the exact opposite. So you're going to do the opposite of each step in the reverse order. So minus 5 came last for the normal function. That means adding 5 will come first for the inverse. And then the opposite of multiply by 3, divide by 3. So to make this inverse of f of x equals, I now have a list of the operations that happen to the input of the inverse. So what I do is I plop down an x because I know that this inverse has to have an input somewhere. So I just plop down an x. Then I do these two operations, x plus 5 divided by 3. That's perfect. The other way you can do this, completely okay to do it either way, is to know that f of x is the exact same thing as y. So I replace it with y there. And then this is the swap x and y method. Since inverses have the inputs and outputs swapped, you can find the inverse simply by switching the inverse and output. So by swapping the input and output right here. So this will become x equals 3y minus 5. And then you just solve for that new y, and you will have the inverse function. So I add 5 to both sides. I'm trying to get y by itself. And then I will divide by 3. And that tells me that y equals x plus 5 over 3. But now that I've solved for y after swapping x and y, what I actually have here is the inverse of the original function. Bada bing. And you'll see, of course, they're the same function. Either method is completely okay. I'm going to wrap this up real quick before it goes more off the rails. This is a function g of x. Let's do and undo and call it a day. Okay, so in PEMDAS order, I pretend that I am this little x, and I'm writing down all of the things that happen to x in this do column. So the first thing that would happen if I were to plug in a number here is it would get multiplied by 5. Inside the parentheses, first thing that happens is that multiplied by 5. I'm still inside the parentheses. Next thing that happens is that add 7. And then the exponent raising to the power of 3. And then the dividing by 2. And then finally, the last thing that would happen for the original function is add 11. So when I make the undo list for the inverse function, I do the opposite of each step in the reverse order. So it'll start with minus 11. And then I work my way kind of up the do column, and I do the opposite for every step. So the opposite of dividing by 2 is multiplying by 2. The opposite of raising to the third power is rooting to the third power, like taking a cube root. And then I'm still working my way up. The opposite of adding 7, subtracting 7. The opposite of multiplying by 5, dividing by 5. So now I have the steps of the inverse function. This is g of x up here, so this will be the inverse of g of x. First thing I do every time is I just plop down an x somewhere around there. And then I will do 1, 2, 3, 4, 5, those 5 operations to our inverse function in that order. So minus 11 is the thing that comes first. And then multiply by 2, so I multiply everything I have so far by 2. And then a cube root, so I take the cube root of everything I have so far. And then I subtract 7, but make sure, I already cube rooted, so make sure this minus 7 doesn't go under here. It'll be on the outside, just like that. And then finally, everything gets divided by 5. That's the last thing in my undo column, so that is the inverse. Okay, awesome. I feel like I butchered these explanations, so if you want to check out other videos on inverse functions, that might be helpful. I'll see y'all on Monday, and before the test, we can talk about any of this. If it's confusing to you, we can practice more before we take it. I'm sure y'all are going to do great. Let's get it, let's get it. And I'll see y'all then.